In 1999, NASA faced a stunning setback with the loss of the Mars Climate Orbiter, a spacecraft valued at $70 million. The mission was intended to study the Martian climate and atmosphere, but a seemingly minor mistake had catastrophic consequences. A simple unit conversion error, confusing metric units with imperial measurements, caused the spacecraft to enter Mars's atmosphere at the wrong altitude. As a result, the orbiter was destroyed, never fulfilling its scientific purpose. This incident not only cost millions of dollars, but also cast doubt on NASA's operational procedures and threatened the agency's reputation. The disaster became a cautionary tale about the importance of precision and communication in complex engineering projects. In the late 1990s, NASA stood at a crossroads, facing intense scrutiny from both the public and government officials. The agency was under immense pressure to deliver successful missions as previous setbacks had cast doubts on its reliability. Against this backdrop, the Mars Climate Orbiter emerged as a beacon of hope. Scientists and engineers invested years of work, believing this mission could unlock new insights into the Martian atmosphere. Expectations ran high, with many viewing the orbiter as a crucial step toward future exploration of the Red Planet. The stakes were enormous, and every detail mattered as NASA prepared to launch one of its most ambitious projects yet. The Mars Climate Orbiter was the result of many years of meticulous engineering, innovative design, and substantial financial investment. Teams of scientists and engineers collaborated across disciplines, tackling complex challenges such as propulsion, thermal control, and data transmission. Each component underwent rigorous testing to ensure it could withstand the harsh conditions of space travel and the Martian environment. The project demanded not only advanced technical expertise, but also careful coordination among international partners and agencies. Funding for the orbiter reached hundreds of millions of dollars, reflecting the high cost of cutting-edge space exploration. Every stage, from initial concept to final assembly, was marked by precision and dedication. The Mars Climate Orbiter stands as a testament to human ingenuity and the significant resources required to push the boundaries of planetary science. Within the navigation software, a critical issue lay hidden: the use of conflicting measurement units. Some components operated using feet, while others relied on meters. This discrepancy went unnoticed by the teams responsible for development and integration. As a result, calculations based on these mixed units produced inaccurate data, undermining the reliability of the system. The oversight stemmed from assumptions made during collaboration, where each team believed the other was using the same standard. This subtle error would later have significant consequences, highlighting the importance of clear communication and rigorous validation in complex projects. The spacecraft soared into the sky with remarkable precision, its engines igniting flawlessly and propelling it beyond Earth's atmosphere. Every stage of the launch sequence unfolded seamlessly, reflecting the meticulous preparation and expertise of the mission team. As telemetry confirmed all systems were operating within expected parameters, a wave of optimism swept through mission control. The crew and engineers alike felt a growing sense of confidence, buoyed by the mission's smooth progress. Early data transmissions reinforced the belief that the spacecraft was on the right trajectory, fueling hopes for a successful journey ahead. As the spacecraft journeyed through space, its trajectory began to shift ever so slightly. Small discrepancies appeared in the navigation data, but these anomalies were so subtle that they went unnoticed by mission control. The onboard systems continued to transmit readings within expected parameters, masking the gradual deviation. Over time, these minor errors accumulated, causing the spacecraft to drift further from its intended path. Mission engineers, relying on automated checks and routine telemetry, did not immediately recognize the growing problem. It was only after the drift became significant that the true extent of the issue was revealed. As the Mars Climate Orbiter approached the red planet, NASA engineers closely monitored its trajectory and vital systems. Suddenly, data streams began to show unexpected readings, hinting at a possible deviation from the planned course. Tension mounted in the control room as teams scrambled to analyze the incoming information, searching for clues to the anomaly. Communication with the spacecraft became increasingly erratic, raising concerns about its stability and safety. Then, without warning, all contact was lost. The orbiter vanished from tracking systems, leaving scientists and engineers stunned and searching for answers. The unexplained disappearance marked a dramatic and sobering moment in NASA's ongoing exploration of Mars. The investigation into the mission's failure revealed a critical error in unit conversion. Engineers discovered that one team had used metric units, while another relied on imperial measurements. This mismatch led to incorrect calculations for crucial spacecraft operations. As a result, commands sent to the vehicle were based on inconsistent data, causing the spacecraft to deviate from its intended trajectory. The error went unnoticed until it was too late, ultimately leading to the loss of the mission. This incident highlighted the importance of clear communication and standardized procedures in complex engineering projects. In the wake of the disaster, the nation grappled with shock and grief, but the consequences extended far beyond emotional impact. NASA faced intense public humiliation as the media scrutinized every detail of the tragedy. Congressional hearings were swiftly convened, with lawmakers demanding answers and accountability from agency officials. The investigation exposed flaws in decision-making and safety protocols, casting doubt on NASA's competence. As criticism mounted, the very future of America's space program hung in the balance. Funding and support were threatened, and the agency was forced to confront the possibility of drastic changes or even cancellation of upcoming missions. This period marked a turning point, compelling NASA to reevaluate its priorities and restore public trust. The failure served as a pivotal moment in the history of space exploration, prompting a thorough reevaluation of engineering practices. In response, organizations implemented rigorous reforms, emphasizing the importance of clear communication and standardized procedures. One of the most significant outcomes was the creation of the Unit Consistency Standard, a global framework ensuring that measurements and calculations remain uniform across teams and nations. This standard has since become a cornerstone of mission planning, dramatically reducing the risk of costly errors. As a result, space missions today benefit from enhanced reliability and collaboration, demonstrating how lessons learned from setbacks can drive lasting progress throughout the industry. The scale of this error serves as a powerful reminder of how even small oversights can lead to significant consequences in high-stakes environments. When the stakes are so high, the margin for error becomes vanishingly small, and the ripple effects of a single mistake can be felt far beyond its origin. This incident invites us to consider how many other failures may go unnoticed, quietly shaping the outcomes of critical missions. Are there lessons hidden in the shadows of these unseen errors, waiting to be discovered? The true impact of such mistakes may only become clear with time, challenging us to remain vigilant and reflective in our pursuit of excellence.